As always, please pause the video to give the question some thought before moving on. We are asked to find the critical numbers of the given function. And of course, before we can do that, we have to know what a critical number is. And basically, a critical number is a value of x at which the derivative is equal to 0 or the derivative does not exist. So what that means is that we're going to have to calculate the derivative of this function and then try to determine the values of y, in this case it's y as opposed to x. We have to find the values of y at which the derivative is equal to 0 or does not exist. So our first task is to compute the derivative of this function, and that of course is symbolized by g prime of y. Now we have here a rational function where we have a polynomial divided by another polynomial, and in order to compute the derivative of a rational function, in many cases we're going to have to use the quotient rule. So we'll have to pause the video for a moment and think about what the quotient rule and think about how you would apply it to calculate the derivative of this function. Now I'll go ahead and post what the quotient rule is, and then we can talk about how to apply it to this function. Now most standard calculus textbooks wouldn't express the quotient rule in this form, but it turns out that this will be a little bit easier to understand. So basically all we have to do is take the bottom part of the rational function and multiply it by the derivative of the top part of the rational function, and then subtract the top multiplied by the derivative of the bottom, and put that entire result over the bottom part of the rational function squared. Probably sounds complicated, but once you go through it's not too bad in this case. So we'll go ahead and apply the quotient rule to the function in order to calculate the derivative of the function. So according to the quotient rule, we begin by writing the bottom part of the rational function. We multiply it by the derivative of the top. Now the derivative of the top ends up just being 1 minus 0. And we subtract the top part of the rational function multiplied by the derivative of the bottom, which would be 2y minus 1. And plus 0 as well, because the derivative of the constant is 0. And then we put that all over the bottom part of the rational function squared. Now we're going to have to algebraically clean this up before we can move on. So after the first step of algebraically simplifying it, we have this. The 1 minus 0 is simply 1, and when we multiplied 1 by the y squared minus y plus 1, that just remained y squared minus y plus 1. We have to be careful over here, though. We end up having to FOIL this product because you have a binomial multiplied by another binomial, and the way to multiply two binomials is using the FOILing technique. Now you'll notice that we left a parenthesis around the 2y squared minus 3y plus 1 because we're going to end up having to distribute the minus sign to each term inside the parentheses. And that's a common mistake, is that students often forget to distribute that minus sign through to each term. So we'll have to go ahead and do that. So here's what it looks like after distributing the minus sign, and then of course we're going to have to combine like terms in order to continue to simplify it. So you have a y squared term there and a y squared there term which we can combine, and then you also have a y term and a y term there that you can combine, and then the plus 1 and the minus 1 are actually going to cancel out, so those we can end up disregarding. So after simplifying the derivative, we end up with the following expression. And again, we are asked to calculate the critical numbers of the derivative. The critical numbers are those values of y at which the derivative is equal to 0 or the derivative does not exist. So the way to do that is as follows. When your derivative is a rational function, then you can split the rational function up into two separate functions. So in order to figure out where the rational function in this case is equal to 0, we can actually set the top equal to 0. So we're just going to come over here and set negative y squared plus 2y equal to 0. And this will tell us those values of y at which the derivative is equal to 0. To figure out the values of y at which the derivative does not exist, we can actually take the bottom part of the rational expression and set that equal to 0 as well. So when we do that and solve for y, that will give us those values of y at which the derivative does not exist. So we're going to solve these two equations separately, and those will give us the critical numbers. So we'll solve this one first, and in order to do that, you're going to factor out a y. and then we can split this off and set each factor equal to 0. So we're going to get one answer right here, and then when we set the other factor equal to 0, we'll end up with a second value. So these two values, y equals 0 and y equals 2, are those values at which the derivative is equal to 0, and therefore that makes them critical numbers. Now to find the remaining possible critical numbers, we have to solve this equation here. Now right now you have an expression that is being squared, so to get rid of that we're going to take the square root. And you have to do that to both sides of the equation. Now when you do that, you're left with a quadratic equation, and to solve a quadratic equation you have two choices. You could factor the quadratic equation, or you can use the quadratic formula. It turns out that this quadratic equation is not possible to factor it, so we can try the quadratic formula instead. And let's recall that the quadratic formula is the following. Now when you plug in the values of a, b, and c into the quadratic formula, you're going to notice that you're going to end up with 1 minus 4 underneath the radical. And 1 minus 4 is a negative number, of course, and since the square root of a negative number is not a real number, it turns out that we're not actually going to be able to solve this equation for any real number. So although we had two critical numbers from setting the top part of the derivative equal to 0, setting the bottom equal to 0 does not actually generate any additional critical numbers. And what that means is that the derivative has only two critical numbers, y equals 0 and y equals 2.